Hello friends, today I will discuss the synchronous condenser. In this video, the terms that are used are assumptions, necessity, and the terms used definition, construction and operation, advantages and disadvantages of the synchronous condenser. Here the assumption is that the synchronous motor do not have any rotational losses, that is, the real power drawn by it is zero. So it operates with overexcitation at no load condition, that is, it supplies only leading reactive power to the system, that is connected load, and the necessity is to improve the power factor of three-phase inductive load. And the terms used in this video are overexcitation, synchronous motor, no load, three-phase power factor, lagging load, three-phase AC supply. The definition of the synchronous condenser is nothing but it is an overexcited synchronous motor running on no load, and its construction is like this. So synchronous motor connected to the three-phase AC supply, that is generating station, and this is the three-phase load connected to the generator. This three-phase load, the power factor is lagging and it draws lagging reactive power and real power, whereas the synchronous motor is also connected across the three-phase supply like this. This synchronous motor operates at no load condition with overexcitation condition, so that it takes the leading current, so that it provides the leading reactive power like this, and this can also be written like this. This is the three-phase AC load connected to the three-phase AC supply, and across the three-phase AC supply the condenser is connected like this. This is called the condenser. Condenser is nothing but a synchronous motor operating with overexcitation at no load condition, that is, it takes only the reactive power, that is leading reactive power, and it does not take any real power. And whereas three-phase load is a lagging power factor load, and it draws the real power and also it draws the reactive power. And the current drawn by the three-phase load is represented by IL, whereas the current drawn by the synchronous condenser is IM. Taking the applied voltage per phase of the source as V, the IM value and IL value and I can be drawn like this. This is the applied voltage V per phase, whereas the condenser current IM will lead the V by an angle called phi m, whereas the three-phase load, that is three-phase inductive load, draws the current IL with an angle of phi 2 with respect to V like this, and the resultant of IM and IL is nothing but I. This I will lag the applied voltage V by an angle called phi. The original power factor of the three-phase load is cos phi 2, that is the angle is phi 2, power factor angle is phi 2. But now with the synchronous condenser, the angle between V and the resultant current has become phi, and this phi is less than the phi 2. So the power factor of with angle phi is more than the power factor with angle phi 2. That is, the power factor is improved due to the connection of the synchronous condenser across the three-phase load like this. The same vector diagram can be shown in a magnified condition like this. So this is the origin, this is the applied voltage V, and this is the Synchronous condenser current, that is under overexcitation condition, it acts like a capacitor. A capacitor current always leads the applied voltage, and in this case the angle of leading of current Im is phi m, whereas the three-phase load is inductive load and its current is IL. This is lagging the V by an angle called phi 2, whereas the resultant current Im and IL is nothing but I, and this I will lag the applied voltage V by an angle phi. So this uh, cos of angle phi is more than the cos of the angle phi 2, which is nothing but the load power factor initially. The advantages of synchronous condenser are nothing but the power factor of the load can be tuned to finer value, that is to the required level, with the field excitation of the synchronous motor under no load condition. The second advantage is this synchronous motor under overexcitation condition with no load, it can withstand the overloads across the load for a short duration. Next, disadvantages of synchronous condenser is its initial cost is high compared to the static capacitors, and its operation and maintenance is high. That is, its cost of operation and maintenance is high, and it has the considerable rotating parts and the associated losses which are neglected in the operation, and the efficiency of the synchronous condenser is only 97%. That is, its capacitance, its efficiency is less than the static capacitors. So being the synchronous condenser is synchronous motor, it will have the rotating parts. So as a result, it produces noise during its operation. Since the synchronous condenser is a synchronous motor, so as the synchronous motor is not self-starting, so it requires auxiliary equipment to start it. Similarly, there is a chance of that the synchronous motor is going to be out of synchronism, which leads to the interruption of the supply in the circuit. Let me summarize once. Suppose there is a three-phase AC supply like this, and there is a three-phase lagging load like this. So whose active power is P and reactive power is lagging, that is Q. And across this load, a synchronous motor operating at no load condition with a no load at overexcitation condition, and it is called the synchronous condenser, and it will take the leading current, whereas the three-phase load takes the lagging current, and this synchronous motor takes the leading reactive power and it does not take any real power, and this leading reactive power compensates the lagging reactive power taken by the three-phase AC load. So due to this, the net reactive power reduces, so that the power factor of the load condition improves like this in the vector diagram shown. So here the net power factor angle is phi, which is more than the which is less than the angle phi 2, which is the original three-phase load power factor angle. So the cos phi 2 is less than the cos phi, because the phi is less value compared to the phi 2. So the power factor of the system improved due to the connection of the synchronous condenser across the three-phase load, which is having a load lagging power factor.